Circles omega 1 and omega 2 intersect at points x and y. Line L is tangent to omega 1 and omega 2 at A and B respectively, with line AB closer to point x than to y. Circle omega passes through A and B, intersecting omega 1 again at D, and intersecting omega 2 again at C. The 3 points C, Y, and D are collinear. XC equals 67, XY equals 47, and XD equals 37. What is AB squared? We have two circles here, omega 1 and omega 2, which intersect at points x and y as shown. And then we also have this tangent line L, which is tangent to both omega 1 and omega 2 at A and B respectively. And it's closer to x than to y. So it's going to be on the top side of this diagram. There we go, let's call those A and B. Now we also have circle omega, which passes through A and B, but it also intersects circle omega 1 at a different point D, and intersects omega 2 at a different point C. And the question is asking if this figure is constructed in such a way that C, Y, and D are collinear, meaning they lie on the same line, and XC equals 67, XY equals 47, and XD equals 37, then we have to find AB squared. So the first thing we want to notice here is that we have three circles, omega 1, omega 2, and omega. And each pair of these circles has two intersection points. For example, omega 1 and omega 2 intersect at x and y, and the other pairs of circles have two intersections as well. Omega 1 and omega intersect at A and D, omega 2 and omega intersect at B and C. So we know all three radical axes of the pairs of circles, since the radical axis of two circles is just the line connecting their intersection points if they intersect twice. So we know that all three radical axes of pairs of three circles are concurrent, and the proof for that is simple. But for now, let's just draw those radical axes. We have DA, and we have the extension of XY. And by this theorem, that's also going to lie on the extension of BC. Here, let's call that point F. And the proof is simple. As I mentioned earlier, we just take the power of F with respect to each circle. So the power of F with respect to omega 1, since F lies on the radical axis of omega 2, it has equal power with respect to omega 1 and omega 2. I meant the radical axis of omega 1 and omega 2. It has equal power with respect to both circles. So the power of F with respect to omega 1 is equal to the power of F with respect to omega 2. But the power of F with respect to omega 2 is also equal to the power of F with respect to omega, since it lies on the radical axis of those two circles, which is just BC. So this implies that the power of F with respect to omega 1 is equal to the power of F with respect to omega. And that means it lies on the radical axis of omega 1 and omega. And that implies that all three radical axes are concurrent at F. So we've now established point F as the unique point that lies on all three radical axes, AD, XY, and BC. And this gives us an advantage because we have triangle FDC now, and we notice that we have the circumcircles of DAY and BCY, where AY and B are points on the sides of triangle FDC. And the circumcircles of those two triangles intersect at X. Maybe we can add a third one, and perhaps that also passes through X, the circumcircle of triangle FAB. Well, yes, it does. That's called Michel's theorem. And X is known as the Michel point of triangle FDC with respect to points A, Y, and B on its sides. This theorem is also easy to prove. So let's prove it now. We have angle AXY, directed angle AXY, is equal to pi minus directed angle D from cyclic quadrilateral DAXY in omega 1. In omega 2, we have cyclic quadrilateral CBXY, which gives us directed angle BXY is equal to pi minus directed angle C. So if you add these up, you're going to get the sum of angles AXY and BXY, which adds up to be more than 180 degrees. So it's an obtuse angle, more than pi. So we have to use 2 pi minus angle AXB instead of simply using angle AXB itself. So we have 2 pi minus angle AXB, and that's equal to 2 pi minus directed angle D plus directed angle C. And so we know directed angle AXB is equal to the sum of angles D and C, which is just pi minus angle F, where angles are taken with respect to triangle FDC. And the reason it's pi minus angle F is because the sum of the angles in any triangle is pi. So we have directed angle AXB is equal to pi minus angle F, and that actually implies that quadrilateral FAXB is cyclic. So this was just an overview of Michel's theorem, where X is the Michel point here, with respect to triangle FDC and points A, Y, and B on its sides. So we know that this quadrilateral is cyclic. Let's call its circumcircle FAXB omega 3. So now what can we say about this diagram? Well, we have an unnamed point here, which is the intersection of FXY and AB. Let's call that G. Then what can we say about G? Well, we know that the power of point G with respect to omega 1 is equal to GA squared. And that's equal to GX times GY, which is also the power with respect to omega 2. And that's GB squared. So GA squared equals GB squared. Because neither length is negative, we conclude that GA equals GB. But we also have that GA times GB, which can equal any of these three things. If we look at circle omega 3, well, we know we get that GA times GB is equal to GX times GF. So we have GA times GB is equal to two things. It's equal to GA squared, since GA equals GB, which is equal to GX times GY. That's the first thing. It's also equal to GX times GF. And since GX is not equal to 0, we can divide the two equations, and we get that GY equals GF. So we have two things. We know that GA equals GB and GY equals GF. And that actually implies that quadrilateral FAYB's diagonals bisect each other where they intersect at G. That implies it's a parallelogram. So we can label the parallel sides. We have this pair of sides is parallel, and this other pair of sides is parallel as well. This new finding of a parallelogram in FAYB, along with the cyclic quadrilaterals, gives us a chance to find more equal angles. So if we start doing some angle chasing in omega 1, we know that, let me use this color, this angle DAY on this side of the parallelogram, you can extend that to F, and it'll equal this angle because lines AY and FC are parallel. But you can also write it as this angle over here because lines DF and YB are parallel. So all three of those angles are equal. Let's do another equal angle. We have that angle D here is equal to this angle BYC. And that's because lines FD and BY are parallel. And obviously, DY and C are collinear. And then the final pair of equal angles that are present here is this one. Angle AYD here is equal to angle BCY, this one. Because AY is parallel to FBC. And now we have the black, red, and blue angles. We can use that to create more angles than just these. We know that the sum of the black, blue, and red angles is pi, because that's just the sum of the angles in a triangle. However, the sum of the angles here along DYC is also pi. So we can extend this to equal angle AYB, because the sum of these three angles is pi. And also due to tangent stuff, angle ABY from the tangent at B is equal to angle BCY, which is a blue angle over there. And the other one, angle BAY from the tangent at A, is a red angle, like angle ADY. So we actually have three similar triangles now. Let's write them down. We're going to go in the order red, black, blue for each triangle. We have triangle DAY, is similar to triangle AYB, which is in turn similar to triangle YBC. So we have a nice progression of 3 triangles here. And we want to find AB squared. So we want to get some similarity ratios here that have AB in them. So if we look at the first pair, we have dy over AB. But if we look at the second pair, second and third, we have that's equal to AB over CY. So dy times CY is equal to AB squared. And so, after all, it just turns out that the quantity we want to find, which is equal to AB squared, is nothing but dy times CY. Now, how can we find that? Well, we suspect it has something to do with Stewart's theorem in triangle, XDC. But clearly there's got to be some equal angles we can use to get a nice ratio of lengths in dy and cy, right? Well, it appears as though the 2 angles are equal. It certainly does. But let's prove that xy bisects dxc. Well, that's easy. We just have the black angle here in cyclic quadrilateral daxy, which can be moved over to here. And then we have another black angle cby in omega 2, which can be moved over to here. cby and cxy are equal. And so at first it looked like the 2 angles were equal. Now we have proved that the 2 angles are equal, so we can use the angle bisector theorem to get the ratio of lengths dy and cy, which happens to be xd over xc, which is 37 over 67. So we can let dy be 37x and let cy equal 67x. Now we can use Stewart's theorem in triangle XDC, and the quantity we want to find is dy times cy, which is AB squared. So let's do Stewart's theorem. We have man plus dad equals bomb plus sink. 37x times 67x times 104x plus 47 squared times 104x is equal to 67 times 37x times 67, which is 67 times 67 times 37x plus 37 times 37 times 67x. And so we can factor out a 104x on the left side. We have 104x times 37 times 67x squared plus 47 squared. And we can factor out 104x from the right side too. We can break this up into 2 67 times 37 x's. We have that this is equal to 104 times 67 times 37x. And so by canceling out 104x from both sides, we have that 37 times 67x squared plus 47 squared equals 37 times 67. And what we want to find is dy times cy, also equal to ab squared. And that's equal to 37x times 67x, which is just 37 times 67x squared. And so we move the 47 squared to the other side to get 37 times 67x squared, which is ab squared, equals 37 times 67 minus 47 squared. And so ab squared is equal to 37 times 67, which is 2479, minus 47 squared, which is 2209, and that's equal to 270. Thank you for watching, and please follow my channel if you would like to see more videos.